guys have lab today. That's a two-part lab. First, you'll be doing the electrostatics lab. That's a pretty straightforward activity. I think it's highly conceptual. We have lower level classes do it as well, but you guys can get a lot more done in one lab period. So in addition, you'll have a short second part to the lab, which is the charging by induction. You'll find them marked as parts A and B of the same lab in your lab manual. So that's what you'll be up to today. I should also briefly mention that I've tried my best to accommodate students in the class that really need it, and the lab's wound up pretty full. I realize that's not the best learning environment, so there is sort of a workaround. If you would like to have a little bit more breathing room and a little bit more space to work, I do have a lab for another class Thursdays from 12 to 3. So if that's a time that happens to work for you, you might be able to arrange that you come in for during that time. The only issue we'd have to work around is that you wouldn't be there for the 10 to 15 minute lab introduction during your lab on that you would normally get, and so you might need to still go to that on Wednesday. But keep that in mind. If you prefer to do the lab Thursday 12 to 3 with the lab intro as usual on Wednesday, so basically you pop in for a few minutes and then come back on Thursday. If that's something that you're interested in free, let me know and we'll figure out a way to work out the logistics. Again, this is something where if you feel like your lab is currently too crowded and you're not getting as much out of lab as you would like, it's kind of like a hack to work around that. And I think in future semesters we'll plan on having 3 labs, so this won't be an issue again. I'm not sure where all the people came from that needed to add the class, but I'm always interested in accommodating everyone I can because I know you guys need to transfer, get out of here. So apologies for those of you that feel like it's a bit crowded in there. Are there any questions before we jump in? Okay, so let's get back to what we were doing. We were working on a finite line charge. It has a uniform charge density, the linear charge density. I've given it a length of 2d, just so that it can go from minus d to d along the y-axis. And I'm trying to find the electric field in the perpendicular bisector. So just to give you a recap, on the perpendicular bisector, we found that the y components of the electric field are going to cancel. Because you're on the perpendicular bisector, you always have an equal amount of charge above you and below you. And so whatever charge is above you, creating a downward y component, is going to be exactly canceled by the charges down here, which are going to make a component the other way. So we work smarter, not harder. We don't bother to integrate the y component of the field. In fact, I've left it off here entirely. I crossed it out to 0. That's again only true on the perpendicular bisector. I have to save you some fun for the homework. So if you're not on the perpendicular bisector, you do have to integrate that. So what I do have remaining are the fact that the x components are all reinforcing. Okay? And in fact, one of the very last things I did at the end of last lecture was that instead of integrating from minus d to d, I'm going to integrate from 0 to d and multiply by 2. That's of course because these two contributions from these two charges will be identical, and so I just integrate half the thing and then multiply by 2. That's just easier for me to plug in a 0 and then multiply by 2. And then we have a bunch of constants out here. Of course, k is always constant. That's just a constant in general. This happens to be a constant, not a function, so I was able to factor that out because it's a constant charge density, not just some function of y. Otherwise, I would have had to leave it in there. X itself is also constant. Of course, no matter which bit of charge I'm talking about here, they have the same horizontal distance to the point in question. And then, of course, I'm integrating over y because I have different bits of charge along the y-axis. I do also have x in here. X is, of course, I can't just remove it, but this is a constant. So it happens to be in the integration, but this is still a constant. I can't just factor it out, even though it's a constant like I could this one. So that's pretty much where I left off last time. It may not look exactly the same, and I think I didn't put the dots here for multiplication, but essentially that's where we left off last time. So let's just go ahead and finish it off, get the answer, and then kick it around a little bit and see that it makes sense. So I mentioned that the strategy you take to do this would be a trig sum. You can make your calculus 2, is it calc 2 that you did this?
Yes, sir.
Calc 2. You can make them proud by knowing how to do this. For me, you can refer to the integration table on the last page of the formula sheet, and I'll just tell you what the answer is. And let me just tell you, just write it down here. So this ends up being y over x squared, square root of x squared plus y squared, and of course I have to evaluate over the bounds. And don't forget that you're plugging in for y, not for x. X is a constant. Before I even do that, let me go ahead and bring in the constants in the front. I have what? I'll put in 2k lambda x I hat. I don't know why I changed around the order. I just felt like it. They're all multiplied. And then I noticed that I can at least get this x to cancel with one of these. So might as well cancel that off before I ever evaluate the integration bounds, because it just gives me less to do. So what do I get? I get 2k lambda I hat. I go ahead and I plug in my integration bounds. First I plug in b. Like so. And then the other one, hopefully you can see that it will turn out to be 0. There's a y in the numerator, and that's going to kill the whole thing. So there is my electric field. And I'm going to go ahead and just copy down a little meter. What is my electric field on the perpendicular bisector? It is a function of where I am on the perpendicular bisector. It is still a function of x. So 2k lambda times b I hat over x square root of x squared plus b squared. So there's the formula. It tells me what the electric field is. It always points in the I hat direction. Okay? So this right here, it points in the plus x direction, but it does weaken with distance. You can see that as x increases, that's going to weigh on the denominator. So as x increases, the magnitude or strength of the electric field will diminish. Which, again, makes sense, right? If you move further on the x-axis, you're getting further away from this bar of charge, right? Okay. So this formula right here, this is available for you on the equation sheet. So you don't have to memorize it. If you ever have need for it, you can just grab it. You don't even need to do all this integration again. You can just use it. There are several different ways that you may see it cosmetically different. So don't be tripped up by that. Here's a couple variations. So cosmetic variations. It really depends on the specifics. First of all, many problems they will give you the length of the bar not as 2D, but as just L, okay? So you may see that L is used instead of 2D. So that means what? It means that anywhere where you see a D, like I have in my expression, you would plug in L over 2 instead, right? So it's going to look a little different. Another cosmetic difference is instead of seeing it expressed in terms of the charge density, you may see it expressed as in terms of the total charge. I mean, that's the definition of lambda. It's the charge per length. So you may not see lambda in there. You may see the total charge Q, and then of course the total length, and that might be 2D or it might be L, right? So those are other ways that it might be different. For example, you can see if I solve this for Q, Q would be lambda times 2D. Well, lambda times 2D is actually in the numerator. It's right here. This stuff actually is the charge. The entire charge. So you may see this instead as KQ times I hat over this jump. So that's the same formula. It's just expressed in terms of the total charge instead of the charge density. So don't get tripped up, okay? There's no difference. And then finally, I should tell you that there's another way to express the constant K. So K is, of course, the Coulomb's constant. We've seen it in Coulomb's law. There's another way to repackage that constant in terms of this other constant called epsilon naught. So we already learned that Coulomb's constant was 9 times 10 to the 9 Newton meter squared per Coulomb squared. That's the only way we've seen this packaged up thus far. But for reasons that will become apparent later, you may want to express in terms of K instead of this other constant. You can solve for what that other constant is in this expression. If you work it out, this ends up being 8.85 times 10 to the negative 12. And then, of course, the units, well, they're just going to be the flipped units of Coulomb's constant, right? So this will be Coulomb squared per Newton meter squared. Now, why would you want to have two different ways to phrase the same constant? We'll get to that later, but for right now, I want to kind of bring it into the fold relatively early so that if you ever see epsilon naught, you're not totally freaking out. It's just another way to express K. K is called Coulomb's constant. This is called the permissivity of free space, which is a highly suggestive name. We'll get into why it's called that later. Sometimes you'll see it as permittivity of free space. Permissivity or permittivity of free space, same thing. For right now, it's just a fancy name for this constant, which is a repackaging of Coulomb's constant. I just want to give you a heads up that these are different variations, cosmetic variations on how you'll see this equation and other equations. Right? You can express them all in terms of K or epsilon naught. You can express them in terms of total charge or charge density. There's different ways to measure, characterize the lengths. Okay, they're all the same basic deal. Okay. Okay, so that's my equation. And what I want to do now is I want to kind of take it for a spin and see what I can find. Are there any questions on the integration before I clear the little space? Yeah.
Can we just switch to the formula?
Yeah, so this is on the integration table. So anything, the rules of the game are if it's on the equation sheet, you can just write it down. You don't need to justify it. I don't need to see you do the trig stuff. You can make your calculus instructor weak that you don't know how to do the trig stuff, but for me, you can just use the integration table. Are there any other questions on the math before I clear some room? sketch of the electric field. The electric field, let me zoom out a little bit. We said it always points like this. We also said it gets weaker with distance, and of course the way that we represent that graphically is that the field lines get further apart. So that might look something like this. So on the perpendicular bisector, the electric field always points radially away, but it's getting weaker. And we can pretty much fill in the whole thing. Looks something like this. It really shouldn't be surprising because it's not that different from a point charge, right? A positive point charge, the electric field points radially away. Well, now we just have a bunch of them, so it's not surprising to see that the electric field points generally radially away, right? The details of the exact electric field might be different, but the general picture is like this, right? Now, I should point out that if you zoom out and you start to see that this bar of charge to you, you can barely tell it's a bar anymore because you're far enough away that it essentially starts to look like a blob, right? This is like if you see headlights in the distance, oftentimes you can't tell there's two of them, right? You just kind of see a big blob of light, okay? So what we expect is that if you zoom out enough, we should see that the electric field sort of goes back to that of a point charge. So that's the first thing I want to test. So any finite point charge, so any finite amount of charge of any shape, if you go far enough away, it should converge onto point charge behavior. Far enough away, it converges to a point charge field. Nearby, yes, you might have some differences in the exact value because the shape of the charge isn't a point charge. That's for close by. But when you get far enough away, as long as there's a finite amount of charge, it starts to kind of all blob together. Does that make sense? So that means that the very first thing that you should do once you've done one of these tough integrations is if you have a distance parameter in your equation, you should take that distance, make it very large, and make sure that your formula converges on a point charge. So let's try it in our case. So I'm going to have that x becomes very, very large. So remember, my formula was specifically only good for the perpendicular bisector, but I'm really, really, really far away on the perpendicular bisector. So if x is large, what does that mean? It means that x is much, much greater than d. How far I am away is way, way, way larger than the dimensions of the bar itself. So I'm over here somewhere. This is x. And d, which is half the length of the bar, we see that there's no comparison anymore, okay? So to us, the bar is starting to look like it has its length doesn't really matter anymore. And how does that affect my equation? Well, x squared plus d squared, well, you're adding a giant number x squared plus a smaller number d squared. This is approximately equal to what? Just x squared, that's right. So the d squared becomes negligible. So let's try it out. This one is definitely the easier form to look at. Here I have a d and an x kind of stray separate by itself. So I'm going to grab this formula right here, and what do I get? Basically, I ignore the plus d squared in the denominator. I guess I can write that here. I'm going to essentially ignore this. And what do I get? I get just square root of x squared. That's x multiplied by another x. KQ over x squared. There it is. There's your classic point charge behavior. So far away, the field of this thing is indistinguishable from a point charge with the same amount of charge. Doesn't matter that we've kind of smushed this into a kind of a line. If we're really far away, those details don't matter. Does that make sense? Question?
Get to get rid of the I hat.
Oh, I was just doing the magnitude. So
Okay.
yeah, we can put I hat here if you want.
I don't know.
I didn't say what I was working on, so I guess that's the vector. Question?
How come the D in the charge doesn't go to zero? But the-
Here, we mean like this one?
yeah.
Well, this one's just more awkward to figure out what would happen. This becomes negligibly small, right? What you'd have to do is, this becomes small, but what that would tend to make you think is that the whole thing went to zero, right? Right, if D is tiny, then this whole thing would be to go to zero, which I should say is not wrong. If you go really, really far away, the electric field does go to zero. But the problem is I want to see what does it look like before that, right? So this, if I let x go to zero, this does go to zero. But I want to see the dependence on x before it does that, right? I want to see that it converges onto a point charge behavior before it basically goes to zero. So it makes it harder to see here what happens. It's just harder to take the limit, so to speak. If you are more careful mathematically, you could do the same thing, but I just use this one because it's really easy to take the limit. Does that sort of make sense? Okay. Any other questions? So yeah, if you have alternate formulas, always grab the one that's easier to work with, and where the limit is, it's easy to see what happens. Yeah.
Is the reason why D becomes zero is that when you zoom in, like D becomes really small.
When you zoom out, you mean?
Yeah,
Yeah, it's just that D is fixed, right? The length of the charge is the length of the charge. You can't change that. But it looks small in comparison when you go to a very, very large distance, right? So you're asking what's the electric field at a very, very large distance, then X looks much larger than the certain fixed length of the bar. Okay, and I do emphasize that this is any finite line charge, okay? So this is in contrast to what I'm going to do next, which is I'm going to look at a geometry where I extend this in both directions. Okay? So let's do that part. So now I'm going to look at is an infinite line charge. So I'm going to let the ends go very far away. Essentially, I'm going to let D go to infinity. And you might point out that if that has infinite length, isn't it going to have infinite charge? Yes, it is. However, what I do want to do is keep their ratio the same. So I'm going to keep lambda, which is their ratio, a constant. So this is one of those things where you know your math instructors hate how loose we are with this stuff. I'm saying infinity over infinity is a constant. Okay. So I'm extending this line out, but I am making sure as I extend it out forever that the density of charge on it is even. Okay. So let's first figure out what happens with the equation. Now here, I'm going to cherry pick exactly the other way. I don't like this one anymore because this one has the total amount of charge, and the total amount of charge is now infinite. Instead, I'm going to pick this one because lambda still makes sense. So let me show you what happens with this formula. So first, let me just write it down. 2k lambda d I hat over this stuff so that's just my raw formula. I've just chosen the one that seems to be better suited towards this weird infinite geometry. And then I'm going to make the opposite point, that in this case, x, no matter what it is, so however far away I am from this thing, it will never be as far away as the ends of the bar, because I've taken the ends of the bar forever, out forever. So it looks like this now. So no matter how far I am, x, away from the bar, it's not going to be nearly as big as the ends because the ends have been taken out forever and ever, okay? So then it allows me to say that x squared plus d squared is now approximately what?
T squared.
D squared. Not x squared anymore, d squared. So it's basically the exact opposite limit as I just did. Here I said that x dominated because I was really far away from a finite bar. So the bar didn't get bigger, I just got further away. Now I've made the bar super, super long, so no matter how far away from it, it's not that far. So let's go ahead and evaluate here. Now I'm going to knock this to 0. And what do I get in the denominator? I get square root of d squared. So that's d, which luckily cancels with this d, because otherwise that would have been infinity. So it actually gets rid of my problem entirely. I get 2k lambda over x. Wait.
What about the x? Doesn't that also go to 0? So you have
Well,
something over 0.
I didn't say it was 0. I said it was small in comparison to d, right?
Okay.
But I can leave it alone unless it's added or subtracted from d, right? So I don't have to worry about the x, right? It's just if you ever have a situation where a small number and a big number are added, the small number is negligible, right? I don't have to otherwise touch it if it's not presenting a problem, right?
So that's the only time we can say that x is approximately 0.
Right, it's 0 in comparison to d, right? So it's like if you have like 1 plus a billion, okay? It's not that that's 0, it's 1, but this is still approximately a billion, right? So anytime you have a small number plus or minus a large number, the large number is the one that matters, okay? So what do we have? We have a formula for the electric field of an infinite line charge. So this is an infinite line charge of uniform charge density. So that's one expression right there that you will see. That's in terms of k. And you can also do it in terms of the epsilon naught. So again, remember that you can replace k with 1 over 4 pi epsilon naught. So this looks like this. And the 2 in the numerator cancels a little bit with this 4, so that's why there's only a 2 left in the bottom. Okay? So this is our first electric field that is not expected to have the proportionality of a point charge. Notice that this is not 1 over x squared. Remember that that was expected only if you have a finite amount of charge, okay? The amount of charge on this thing is infinity. Instead, it falls off slower than that. It falls off as 1 over x. So as far as how is it that it falls off slower, well, I'll give you a little bit of a motivation as to how that can happen in a little bit. But for right now, realize that if you have an infinite amount of charge, it is not going to fall onto point charge behavior very far away, because no matter how far you are from this, it doesn't matter if you're 1,000,000 miles away, it does not converge into a little blink blob of charge. It's not a little point anymore. You will always see it as an infinite line. No matter how far you are away, you will see that this thing goes all the way to infinity. Okay? So let's go ahead and draw the whole thing. I'm going to go ahead and recognize that it's something more or less like this, except for the field is never going to wrap around like this because there's no end that you can wrap around. So let's fix this. I guess I'll just erase the whole thing. What does this look like?
Just radial to the side.
So it looks like this. I should mention now that there is no perpendicular bisector. Where's the middle of a line that's infinitely long? Okay? Does this make sense? So really, we haven't just found this on the perpendicular bisector, even though that was the original kind of derivation here. We've actually found it for any location. Okay? So this is not just the perpendicular bisector. In fact, it is any location. Any location has equal claim to be the perpendicular bisector for an infinitely long line. So for instance, if I pick a random point right here, I have every expectation that the electric field points like this. Why? Because for any charge down here that would tend to create a positive y component, there will be another one over here that creates a negative one. They'll always be paired up. So no matter which charge you're looking at, or which point you're looking at, there will be just as much charge above as below. That's the beauty of an infinite line. Okay? So in fact, a lot of times, instead of calling it x, we just rebrand this as the radial distance. So I think on the formula sheet, you will find this not in terms of x, you'll find this in terms of r. So the electric field will be, let me just put the magnitude here, 2k lambda over r, or lambda over 2 pi epsilon naught r. Okay? Where r is just how far you are away from the line. Now, I've just drawn one perspective of this line, but I want to caution you that the way that I've drawn my figure at the moment is a little bit dangerous, because these field lines appear to be equally spaced. So what would that seem to indicate when you have equally spaced field lines?
Equal.
Uniform field. Is this field uniform? No, it actually dies with distance, right? It's proportional to 1 over r. It might not die as fast as a point charge, but it certainly dies off. The field lines are getting further apart. You just can't see them, because I did a drawing where that's hard to see. So I'm going to try to draw a little bit better of a head-on view. So this is head-on. So that's not a point charge. That's just a, like, you see what I'm trying to draw? It's like that. Okay.
Seeing it from the top. Okay.
What's that?
Top of the bar, you say?
Yeah, exactly. So I'm imagining an infinite line that's coming straight toward me. It pierces my eyeball, goes right out the back. Keeps going, okay? So there, you will see that the field lines get further apart, indicating that the field is weakening. So the symmetry that this thing has is what we call cylindrical symmetry. Cylindrical symmetry. I'm afraid to ask now, where did they talk about cylindrical coordinates?
Calc 3.
Calc 3?
Mm-hmm.
They don't even get to that until Calc 3? All right. So, in cylindrical coordinates, instead of x, y, z, you have r, theta, and z. Okay? So r is radial distance. So it's how far you are away from this thing. Theta is circumferential. So it's going around. And then z is what we call the axial. So when something has this geometry, these are the three ways you can specify where you are. So r is how far you are away. Theta is where are you around the thing. So r is this distance. Theta tells you where you are around it. And then z, I can't draw that in this one, but z is how far you are along the thing. So z is like this. So that's another way to specify where you are instead of just x, y, and z. And this has more symmetry to this particular type of geometry. Okay? So for us, out of these three things, two of them don't matter. This is only a function of r. So the only thing that matters is how far you are radially from the bar. The angle does not matter. If you look at it, why should it matter if you're over here versus over here versus over here versus over here? Yes, the direction of the electric field might change, but the strength of it isn't. Why should it matter if you were 5 meters away in one direction versus another direction? Right? The only thing that matters is your proximity to the line, right? So the theta doesn't matter. And likewise, it should not matter where you are along the bar, okay? So no matter where you are, it's an infinite line, so every part is the same as every other part, right? And that's, by the way, why these electric field lines look equally spaced. Because the electric field is equally strong no matter where you are along it, okay? So here, the electric field has no z dependence. So that's why we can't see that the electric field lines are getting further apart, because they shouldn't get further apart along the z, right? They shouldn't get further apart as you move along the line at a constant distance. But remember that these aren't all the field lines. There are other field lines coming from the bar that go off at an angle like this, right? You can see those here. And they are getting further apart with distance, right? So it is weakening. In fact, it's weakening as 1 over r. Okay? So the field lines do get further apart, but you sort of need to be looking from the right perspective to see that the field is weakening. Okay? Does that make sense? So again, I know for those of you that have not seen cylindrical coordinates, this might be a heavy lift, but again, out of the 3 cylindrical coordinates, 2 of them don't matter. The only thing that matters is how far are you away from the bar. It does not matter where you are, in which direction you go. It does not matter walking back and forth along the line either. The only thing that matters is how far you are away from it. Okay? Are there any questions on that?
Professor?
Yeah.
So does that apply to the other bar that is not the finite amount of bar? Because
no, definitely not.
Definitely
right?
not.
Because if you had the finite bar, okay, we only found the electric field at one point, the perpendicular bisector.
okay,
Right.
I see.
So you will find that as you go around this thing, right, you will find some differences in the strength of the field, right? So it's only you might wonder, why would we extend this bar to infinity? There's no such thing as an infinite line charge, right? The universe wouldn't fit an infinite line charge. Well, there are line charges that are very long, where this formula is an excellent approximation. That's the game of physics, right? Is you get a formula that's highly good. And when you make the bar infinitely long, the electric field is much simpler, right? This is not as simple as this, right? So if you have a bar that's long enough, then you can use a simpler version, okay? Are there any other questions? And you'll find on the homework that it spells it out for you. Either it gives you a finite length or it tells you it's very long, okay? So it shouldn't be weird which one to use. So I'm going to actually go ahead and start by cataloging my results so far so that I can add my new results to them. So how does the magnitude or strength of my electric field vary with distance? Well, a point charge, it falls off as 1 over r squared. But we have just done our, and by the way, that's a point charge, and then any finite charge, if you go far enough, it should converge onto that. But we've now done our first infinite charge geometry, and that falls off slower. So this goes as 1 over r, that's the infinite line charge. Okay? So we'll be adding to that chart as we introduce other instances of charge distributions. So let me do another one. The next one is not going to be nearly as challenging. In fact, I think I'll probably be able to finish it today. Again, remember that I'm going to do these charge distributions in the order that I think makes the most sense, but that doesn't mean that the math is the easiest. This next one is, the math is going to be very easy. I'm going to do a ring of charge. So it looks something like this. Whoa, let me try that again. That went horribly.
I got that on camera. Oh, nice.
So I'm going to have a ring of charge. I'm going to give it a radius r, and I'll use capital R here, because lowercase r's are already being used for something else in Coulomb law. So this is r. And I'll give it a total charge q. Of course, you could also define a lambda for it. You would just take lambda, that's the total charge over the total length. What's the length of a circle?
Length?
2 pi
2 pi
r
r.
circumference, right? So if you wanted to express it in terms of lambda, you could. It's going to turn out that that's not terribly exciting, so it won't bother. That's why I put it in parentheses, just for your reference, in case you ever need to do that. And I'm looking for the electric field again on the, I guess I'll call it the perpendicular bisector again. So this right here, this is my plus x-axis. And what that x-axis is, it passes right through the middle of the ring, and it's perpendicular to the plane of the ring. You see what I mean there? The perpendicular bisector. So this axis pierces the middle of the ring, and it's perpendicular to the plane that the ring lies in. So let's go ahead and do it. I want to know the electric field out here. So the electric field out here, let's just take a random Joe Schmo charge here, a little DQ, and figure out what that charge would contribute. So this charge is the distance r away. It contributes something like this, dE. And that, of course, has two components, dEx, dEy. I should also label x is how far away I am, and I'll call this angle theta. So you can see the setup is more or less the same. So, first of all, one of these components I shouldn't bother with.
R.
Which one?
R.
Why?
Because it's uniform wherever you go.
That's right. So for any DQ that I have up here, that would make a contribution like that. There's going to be one down here that cancels it. If there's a bit of charge out here on the ring, there'll be one out here, right? They'll be symmetric. So these will cancel eventually. So who cares? Work smarter, not harder. So all I'm going to do is I'm going to integrate the x contributions, because those will reinforce. All of these bits of charge on the ring, no matter which ones they are going to contribute away from themselves. Okay? So let's do it. So I'm going to have dE x is dE cos theta, and this dE here is going to be k dq over r squared. So r, that's how far I am away, and I can notice that r is going to be square root of r squared plus x squared. Right? That's just Pythagorean theorem. Like so. And then I might as well point out that cosine of theta, that's going to be x over that stuff, right?
I agree.
So let's put it all in. K dq, and I'll just go ahead and combine all this stuff for the interest of time savings. So that's what I get there. And try it yourself if you don't see it immediately, trust me. And now we're going to integrate. So my electric field will be integrating all this stuff. So now I have to decide what's constant and what's not constant. Well, guess what? Everything is constant, okay, except for dq. So x and r are the same for all the dq's. None of them matter, right? Every single dq, no matter who you are, that's the beauty of a ring geometry. They all have a distance x away from the middle, and all of them are a distance r away from that, right? They're all constant. So, we pull that out, k, x, oh, and I guess I should throw an I hat here, so and what's the integral of dq? When I add up all the little bits of charge.
Q.
It's just the whole charge of the thing. So, just like that, I'm done. Remember I said I wouldn't do them in order of difficulty. This is the easiest one by far. So there it is. That's my formula for the electric field on the perpendicular bisector of the ring. So first, let's give it our standard tests. If we get really far away, and x is much, much greater than r, So we are very far away. You can see what happens here. That's going to be approximately 0.
X squared.
We get x squared to the 3 halves, so that's x cubed.
X to the 3.
Cancel one of these in the numerator, and we get kq over x squared.
Jesus.
So
Magic.
eventually it does merge onto point charge behavior,
Coulomb's law.
just as any finite charge should. If you're far enough away, you don't care that it's a ring anymore. It's kind of all smushed together and looks like a point. Okay? However, you can also see that if you plug in x equals 0, which means you're at the center of the ring, the electric field goes to 0.
Because everything's canceling out.
That's right, because everything is canceling out. If you're in the middle of this ring, any contribution that tends to go like that, there'll be another one that tends to cancel it, right? And if you're in the very middle, then nobody is contributing these forward contributions yet. So in fact, this electric field looks something like this. It starts off as 0, it grows to some maximum, and then as you get farther and farther away, it becomes a point charge behavior again. So one of the questions on the homework I have for you is, where is this maximum electric field reached? Okay, so let's knock off there for today, and we'll pick up the disk and plane of charge on Friday.